Hello, this is Mr. Miller and welcome to video 5A about critical numbers. Actually, in this video we're going to talk about absolute maximum and minimums. We're going to talk about relative maxima and minimums, and we're also going to talk about critical numbers. Let's get started. First, we want to look at several examples of graphs and find their maximum and minimum. Here we have a lovely little function here, kind of a goofy one, but it's our first example. And we want to find the absolute maximum of the function. The absolute maximum is the point whose y value is greater than any other points. It's kind of like the highest point in the graph, if there is one. So in this graph, that would be that point right there. So the absolute maximum is 0, 3. It's kind of like the absolute largest. Now, if we look for the absolute minimum, this function actually doesn't have one. Because if you notice these arrows on the side, that means that the function continues to keep becoming more and more negative, actually going to negative infinity. So there's never a low point. It just keeps getting lower and lower. So there is no absolute minimum. So this doesn't exist. All right, relative maximum. A relative maximum is a point that's larger than the points around it. It might not be the greatest point or highest point ever, but larger than those surrounding it. So for instance, this would be a relative maximum. This is higher than the points around it. So if we count here, negative 1, 2, 3, 4, 5, negative 5, 1 would be a relative maximum. Now, in order to be a relative maximum, the function has to be defined in an open interval around the point. That means for x values around the point, the function exists. So endpoints, we'll see this in a minute, can't be relative minimum or maximum. They can occur inside the domain of the function. So here's another relative maximum here. This point's larger than the points around it. So 1, 2, 3, 4, 4, 1 would be another one. And even though this is our absolute maximum, it's a relative maximum too, because it's bigger than the points surrounding it. So we'll list that one also. So 0, 3. All right, now let's find relative minimum. These are the points that are smaller. So for instance, this one right here. This would be a relative minimum. It's at negative 1, 2, 3, and y equals negative 2. Okay, this one is a relative minimum, smaller than the points around it. So this would be at 2, 0. Okay, let's go on to our next example. Here we go. Absolute maximum, that would have to be this endpoint right there. That's the highest point. So the absolute maximum is at 765. Absolute minimum would be this red point down here. That's the lowest point in the graph. So that would be 1, negative 14. Relative maximum. Well, this can't be a relative maximum because it's an endpoint. So the function has to be defined on both sides of it, and it's not. It's not defined to the right. But this point is. This point right here would be a relative maximum. So at 440. And relative minimum, we have two of them. Right here, this would be at 610. And this one is a relative minimum also. It's the absolute minimum, but it's also a relative minimum. And notice that when I was listing relative maximums, I left this point out. It can't be a relative maximum because it's at an endpoint. The function is not defined to the left of the point. Okay, let's take a look at this one. This one, absolute maximum, well, that would be this top point up here. So we have 4 and 128 over 3, whatever it is. Okay, absolute minimum. This is the lowest point on the graph, so that'd be the absolute minimum. Relative maximum would be that one. And relative minimum, actually this function doesn't have any because both of these are endpoints. It doesn't have a relative minimum, so those don't count. Okay, hopefully we're kind of getting the idea here. Take a look at this function. It continues forever on both sides. it goes to negative infinity on the left, positive infinity on the right. So because it keeps going up over here, it never reaches the highest point. So it doesn't have an absolute maximum. It doesn't have an absolute minimum either because it keeps going down on this side. Relative maximum, that would be that point right there. There is one. And relative minimum would be that point. Okay. Now one last example. You can get into some interesting ideas here. This example kind of blows your mind a little bit. If we look for an absolute maximum in this graph, you're not going to find it. You might think, wait, what about this point? Well, it never actually gets to 4. So there's a hole there. So the function increases and gets closer and closer and closer and closer to 4, but never actually gets there. Same on this side, gets closer and closer and closer to 4. So there is no absolute maximum. There's no value that function attains which is greater than the other ones. So it comes close to 4, but never equals 4. Absolute minimum, that one's no problem here. That one's the absolute minimum. Relative maximum, it doesn't have any. It doesn't have a point that's larger than all the points in its neighborhood. So that's gone. Relative minimum, believe it or not, this is a relative minimum. Why? Because it's lower than the points to the left and to the right of it. So if you move to the left, you're right up here. If you move to the right, we're in the part of the graph that's right there. This point is lower than the ones in its neighborhood. So relative minimum, it would be 3, 3. That point is smaller than the points in the neighborhood. So the function doesn't have to be continuous. It just has to be defined on both sides. So it is defined from values surrounding 3. The function exists on both sides of 3. It's just not continuous there, and that is a relative minimum. Okay, now we want to talk about critical numbers. A critical number is a number where the derivative of the function is either 0 or undefined. And we're going to be talking a lot about critical numbers. So either f prime at that number is 0 or f is not differentiable there. So here's a couple of graphs from the book. Remember, f prime doesn't exist if there's a sharp cusp or corner at the point. So that's an example where the derivative doesn't exist. And notice that the function kind of turns around there. Okay, same thing here. Here's a point where the derivative exists, but it has a horizontal tangent. So f prime is 0 right there. These two kinds of points, numbers where they happen, are called critical numbers. Now, the reason why they're important is this theorem here. If f has a relative minimum or relative maximum at a point, c, then c is a critical number of f. All right, so what that means is if we found all the critical numbers of a function, the relative maximum and minimum are inside that set. And that's what we'll be doing soon. We'll find all the critical points, and once we list them, we'll decide which ones are relative minimum, relative maximum, or neither. Okay, so that's our method of finding relative maximums and minimums. Okay, so here's where we're at. We're going to give you a function, just ask you to find the critical numbers, and because we have a graph, we can tell if they're maximum, minimum, or neither. Okay, so this is a nice smooth polynomial function, has a derivative everywhere. So we're going to look for where the derivative is 0. So y prime is negative 3x squared plus 8x. And we want to set y prime equals 0 to find the critical points. So we got 3x squared plus 8x equals 0. You can use your TI-89 in all of these. I'm just kind of don't have mine, so I'm going to try to wing it here without it. So I'm going to use factoring, which means x equals 0, or if we set that one equal to 0, we get x equals 8/3. These are our two critical points. They're points where the derivative is 0, and if you notice, they are points where the function turns around. At 0, that's a relative minimum. And at 8/3, which is, of course, this point right here, 8/3 is about right there. This is a relative maximum. Okay, let's try our next one. Here we have a nice parabola. To find the critical points, we're going to set the derivative equal to 0. The derivative is defined everywhere. It has no sharp corners or cusps. So y prime equals 2x plus 8. And we're going to set that equal to 0. So 2x plus 8 equals 0. You solve that, you just get one critical number, x equals -4. And that corresponds to the relative minimum right there. Okay, and it's a point where it turns. The function's decreasing, turns around, and is increasing after that. So this is a relative maximum. Okay, no problem. Now, when we don't have a graph, we're going to have to do a little calculus to find out if it's a relative max or minimum, but that's coming. Okay, so this one's a little trickier, only because the function's more complicated. We need the quotient rule. So remember, the quotient rule is gf prime minus fg prime over g squared. So y prime is going to be g times f prime minus f times g prime over g squared. Okay, now we can simplify the numerator. If we do that, we're going to get 16x squared. 16 times 16 is 256 minus 32x squared over the denominator. And if we simplify it, we get y prime is -16x squared plus 256 over the denominator. And we want to set it equal to 0 to find the critical points. Now, a fraction is 0 when its numerator is 0. So essentially we have to hit or solve -16x squared plus 256 equals 0. If you put that in your calculator, you get x equals 4 and x equals -4. Alright, so you can use your TI-89 for that. These are points where the derivative is 0. And they have horizontal tangents. So x equals 4, kind of hard to see here. It's a very gentle kind of peak there. But x equals 4 would be a relative max. And -4 relative min. Alright, we made it to our last example. So here we have a graph of a function, and we can see that the derivative is undefined here. So that's a critical number. We already know the answer, -2. But let me show you what happens when we try to take the derivative of the function. We have 2x plus 4 to the 2/3. So y prime is 2/3. 2x plus 4 to the -1/3 times 2, the derivative of the inside function. So I use the general power rule there. So we get y prime is 2 times 2 is 4. That's going to be in the numerator. Denominator we have 3. This guy is going in the denominator as a cube root. Okay, now we know the denominator of a fraction is undefined for values that make the denominator 0. And if I put in x equals -2 here, 2 times -2 is -4 plus 4 is 0. We'll get 4 over 0. And that's why the function's the derivative is undefined there. The function's defined, but the derivative is not. So our critical point is x equals -2, where the function derivative is undefined, and that would be a relative minimum. Okay, so hopefully you're okay with the vocabulary we discussed in this video, and what a critical number is and how to find it. Here are two for you. So we have two polynomial functions. Derivatives exist everywhere for both of these functions. You have to find the critical numbers and then look at the graph and tell me, are those critical numbers relative maximum, relative minimum, or neither? Good luck.